Okay, so we're getting started. We're gonna make a standard old origami crane. That's the thing, I think. That's where we're gonna start. If I remember how to do it, I keep messing up like again and again and again. But we're gonna imagine that you're like on quarantine or some shit, and you don't have origami paper at home, but you may. Like this is origami paper. I'll show it to you more. If you ever get not used it, well, yeah. If you get into it, I advise you go getting it. It's expensive for paper, but paper is still cheap. Go to your neighborhood art supply store, and they'll have some. I almost guarantee. If they don't, they get it. They got the magic catalog, and they'll have some information and knowledge, and always other cool stuff. Like last time I went, I got these uh, Posca markers. These things are dope. You can do anything with them. So yeah, but this is origami paper. This traditional has white on one side and colors on the other side. They usually have some nice bright colors, and other ones. There's foils and stuff. They're very hard to fold. If you're just getting into it, just get the more normal pack with like 200 sheets for a couple of bucks. Then they also have like double-sided ones. I don't know how much paper left because I use them. Yes, not any. This one might be. Oh yeah, this is double-sided. But you have to pay attention because a lot of this traditional origami stuff only shows up on one side. So that's part of the reason to have only one side with pigment on it. Like, why would you waste all that ink? It always comes in like some sort of cool packaging. Japanese have like the coolest on this stuff. Everyone agrees. Like, I'm pretty sure. And then on the inside, and this is great for those of y'all who are in a quarantine situation and wondering, how am I going to learn more about geometry and math and stuff, you know? And we might have like tests or life or someone in the house who needs some schooling. Who is that? Euclid or whatever said there's no royal road to geometry. Well, you just got to do it. That's what that is. So they have these diagrams. Modular ones are great for learning origami really well, getting your hand skills down, because being modular, that you have to use like a bunch of pieces to make the one thing, but the pieces are all the same thing, so you like get real repetitive. It's really good because the precision that it requires to get effective at making what you want to make is more than you might think, and it can be extraordinarily frustrating. I know very few people who don't get like just want to tear it up and throw it away and give up every time, and you have to slow down and pay attention to what you're doing very carefully to make it past that point. And also, it reminds you that like not succeeding is not the same as failing. You just do it again and you learn each time. Now most of us will be at home with no such situation. What you need for this, for most traditional origami things, is square sheets. That's how it's based. Makes everything easier. And coming up with ideas. So you can make yourself a square sheet. I'm doing a poor job of this. I used to be good at it. A lot of people don't know this simple thing. If you're having trouble with basic stuff, so if you fold it like on the diagonal, right? And if you line up this side with this side, so these two sides are the same. Right? Correct? They line up and match. And when you crease, you line up before you start creasing. The thing with paper is it only likes to be folded one time. Well, it can be folded many times, but once you put a crease in there, that's through. You know, it's going to be there for good. But also, when you crease, you generally make sure you give it a good crease. Like people use their nails, other people have tools. You can find anything that's. There's some safety glasses. I don't know. I would never do it this way, but some people do it. I just use my fingers. Generally, my nails are a little janky long. I think I clipped them for this video. So you line it up. Now, an important thing we're going to notice about that is we're trying to get a square, a perfect square. All four sides the same, all four, like 4 90-degree corners, diagonals that bisect each other at perpendicular angles. These are all properties that you learn explicitly in geometry class, right? But now we can see them in action, pretty much. Boom, boom, boom. So we folded that up like that. Now this part is 90 degrees, right? It's a right angle. And if you got a 90-degree angle one thing, and you've got a triangle going on like that, correct? And the two sides are the same, it's got to be like a 45, 45, 90 triangle. And that would also be the same as a square cut through the diagonal, right? The diagonal of the square would cut it like that. I can lead to some cool math discussion about the length of this compared to the length of these two. I always like telling that story. I don't know. I got time. What else? What else I got going on? Hey, there's a pen. So, if you got to remember this important fact: a squared plus b squared equals c squared. Shoot, how bad is that going to be in there? Let's redo that. I didn't notice that wasn't in the video. You got to remember that a squared plus b squared equals c squared, right? And that's for a right triangle. It is commonly known as the Pythagorean theorem, right? I'm just making sure it's on the sheet. Pythagorean theorem. Don't worry, my handwriting is atrocious. You'll never be able to read it. And it's saying that if this side is A and this other leg is B, the legs are what we call the two right angle adjacent sides of a right triangle, and the hypotenuse is C. If you take the area of a rectangle square form there and add it to the area of the square form there, it will equal to the area of the square form there. It's actually cool. There's a cool number file where this old man tells a story. I'll link it up if I remember. That it doesn't have to be a square necessarily. They have to be similar shapes. That's a pretty neat way he tells it and presents it. Well, that's all well and good, and you have to remember this is all Greek stuff, and they like things in explicit proportions. The world operated in proportion and ratio. That was everything. Music, geometry, philosophy, all those things were done according to ratio. That was just God's way of structuring it, whatever you wanted to call it. Demiurge, or I forget all the other ones. Where was I? Oh, so if you have this square, this side's 1 and this side's 1, correct? And we take the diagonal of the square. That's all we're trying to do. So they know that these two sides are equal, it's a right angle, and they take the diagonal of the square. The question is the length of this side. Right? Well, if we follow this idea, they did not have these numbers. They did not really utilize numbers too well, and that's one of the reasons they didn't advance math beyond their sophisticated understanding of basic geometry. You had to wait till later to get any form of writing, mathematical thinking that looked like this, which included numbers. So there was a combination of different societies in the world. Each had its own element as it grew and expanded. There is complaint within mathematics, and I'm a big complainer on this one, of the dominance of white males in the European part, but it really is true. It's been a global study since its early days, and as soon as one mathematician spotted another one's work and spotted it as good, they took it. They either stole it or borrowed or incorporated it. The best way to do is incorporate it and move forward and grow together. So here we got the square, right? And it's got side 1, diagonal. And let's put it through this Pythagorean theorem. So we got 1 squared plus 1 squared equals some c squared. We'll call it c squared, right? 1 squared is 1. 1 squared is 1. C squared is C squared. Doesn't really change, right? 1 and 1 is 2. And then we have C squared. When we have a square, we obviously do the inverse operation. So the opposite of squaring, or inverse of squaring, is square rooting. This thing can confuse people. Well, someone has questions, we'll talk about it later. So if we take the square root of both sides, C squared equals square root of 2. Whenever you square root a square, you get the number itself. Like, that's the property. You don't even have to think about it. That actually helps on understanding a square root. A square root is the thing, a C, that I multiply it by itself to get C squared. So if I take the square root of C squared, I have C. So C equals the square root of 2. Now, this number itself became problematic for one of the Pythagoreans. There may have been Pythagoras, and there's different stories on it, but someone got in trouble for this one. Everything has to be ratio. So Greeks are fine with this number, 1/2, 3/5. If it can be written as a fraction or a ratio, cool. The structures of the universe work. If it can't, not cool. This number right here cannot be written in our form of mathematical numbers more properly than this. It is the square root of 2. It is not a decimal of 1.4 or 1.2, I forget it, or any of that. It's not a fraction, it is that. Because it's really based on the property. C is the number that we have to take to multiply it by itself to get 2. So the only way to write it as a number without a wacky symbol is to base the whole number system around the square root of 2. Which we do things like that when it's important, like the radians measure for trig is based around pi. Like if we need to, we do it. It's not a big deal. We don't need to here, so we don't. The question though is this rational or not? And what we're going to talk about, okay. I'll get a proof. So a rational number is a number that can be written as a over b, and both a and b are integers. That's just what a rational number is. Integers are like the ones you can mark on a number line. Boom, 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 boom. So, let's see if I can remember this proof, because it's always a fun one to try and remember how to do. It's very short, and it's a proof by, I don't know what they call it. It's a classic way of doing it, and it was a variety of different people they say discovered it. So we're going to call a over b a rational number. Or we're going to call the square root of 2 a rational number. We can call any number that we top over bottom integers. So we're going to say this is what is true. And we're going to operate forth as if it is true. And you can do this in mathematics sometimes if you follow your rules very explicitly. It doesn't mean it's absolutely positively true, but because there could be ways to undermine that truth, but this is a pretty cool one. So we're going to play around with it as if it's such, and the first thing we do is, let's see if I can remember, I think it's a equals b times root 2. And then we, to get rid of a square root, we square everything, right? So that's a squared equals b squared times 2. This can be written as a times a equals b times b times 2. Or, yeah, this will be helpful later. And the next part is a little tricky to get. If we revisit the fundamental theorem of algebra, theorem of, no, arithmetic. Algebra is about roots. Fundamental theorem of arithmetic says any whole number can be broken down into a unique group of prime factors. So when you were in school, or if you were in school or whatever, when you did a factor tree, if you said like 48, you're like, oh, that's 24 and 2. Man, it's been a while since I've done math. 8 and 3, 4 and 2, 2 and 2, right? So that would be 1, 2, 3, 4 2s, 2 to the 4th, and 1, 3, right? It can be rewritten like that. And that's saying the prime numbers, which are, you can kind of see a good example of what prime numbers are. If we take a number and we break it down all the way down to its parts that can't be broken, those are the prime numbers. This number 48 has 4 2s and 1 3. If I did my math right, seems to. And if you take 4 2s and 1 3 and multiply them together, you will have 48. Every single whole number has its own unique set of prime factors. Alright? Now we're going to have to be subtle in our ways of thinking. So you can have things that are either even or odd. Right? When we take any number, whole or an integer number, or well, let's look at this. What's double an even number? So like, let's find a number, even number 8, right? We're going to double it. That gives us an even number, right? No matter what, we take an even number and double it, we get an even number. If we take an odd number and double it, we get an even number. Pretty much every time. I think the way I recognize it is like odd is like an even plus 1, and then you have an even plus 1. So those 2 plus 1s joined up and made the next couple, something like that. So if you double any whole number, your result is even, right? We're good. Up here, we're going to look at these as whole numbers that have yet to be factored, but the 2 is fine. And if we factor them, this would be some number of numbers, which would be either even or odd, prime numbers, right? And that would be 2 times, right? And if we double any number, we get an even number, right? Well, here we have some number of them. We have some number of them, and so that would be even. And then this isn't meaning we double it. It just means like we're adding one more number to the list, right? Because it's how many of these factors, right? So this is the one at the end of the string. So this ends up being odd. That usually for the past few thousand years, this has been true, or this has not been true. Even does not equal odd, so therefore the square root of 2 cannot be rational, right? And there was the student who was in the boat for what they were out doing their Greek. It was the it wasn't the Pythagoreans. I think it was another weird group. I could be wrong. It had like these cults of learning, pretty strange. Person gave out this proof, and then they're like, no, this cannot be, you're going to subvert our church and this is no good, so they threw him out of the boat and he died. Been carried through mathematics, and that some variation of it for quite some time, so it's probably pretty true. Anyway, so we have this 45-45 triangle. We're trying to make a square. Going up there, that gives us like a nice line to double check it on. I find it easier if you turn it over and then you can fold it back this way and you can see it. This is a big sheet of paper, so it's not too difficult. That being said, take your time to focus on what you're doing here. There's no way we can possibly solve the problems of the world in any way with just our mindset not all right. But we can take this second to take a scrap piece of paper and make something pretty out of it, and share in that and find the piece that we might need to work together. Here it is. So we had that one diagonal, and then you fold it the other way diagonal, and you see that these would be called valley folds. And you see these sheets, they have like they diagram them. I can never remember exactly which one's which, but they diagram them. One of them is a dash line, and the other one is sort of another type line, but they'll say the different types of folds in there to do. Valley makes a valley, mountain makes a mountain. It's probably two most common ones. And then you were going to fold it both hot dog and hamburger if you're in schools around here, which is I always get confused on a square one because it's both. But, you know, gets the point across laterally. Flip it over first though. This is the sort of thing that, like, paying attention to your steps, because you will not always remember to flip it over. And what will happen is different than what's going to happen here. It'll be much more frustrating. Way more frustrating. So we folded it like that. We got those two folds. And now you got it all divided up into what? 1, 2, 3, 4, 5, 6, 7, 8 even pieces. Alright, I think they're even. From this spot, you can make the two most common bases you'll see. You'll hear about the bird base or the bomb base. The bird base is like a square, and the bomb base is like a triangle. That's the way I can remember it. So when I'm making the bird base, I'm looking for a square. And I know this is the square I'm actually looking for right here. If I folded it right, if you have it like this, it won't seem right. See how these are going down, and if the folds don't go back and forth, then you won't quite see it right. But if you follow the process and you look here, you can see your square right there. And if you do that, it's pretty easy because these come in right there, and the top will come right down on top. That's just always satisfying. I don't care who you are. So you got like this. You see your square. You bring this point and this point down to here. It should just be right where you want it. The next one's this is what I was forgetting last time. Not this one, but the step after this. We're going to take this side right here and line it up with that center crease. I always make mistakes down here at the tip. It won't cause catastrophic problems in this, but it'll definitely make it less clean. And the tighter you get it, the better the edges are, you know? So we got that, and you're going to do that all the way around, so you do it there. Oh, before we get there, so you don't make that mistake, you want the open part down. This part up here that's not open is up. So do that, all four parts. You notice when I'm doing a lot of repetitive things, I try and put it in the same position as like if possible. Partially because my hands are really pretty bad, like clunky, and I've also torn them up pretty bad. The practice of origami itself helped me stop that, actually. It was a big bump right there. It hurts still. I broke my hand. Got upset after my first year of teaching, and they put me on a do not rehire list. I was very kind of them. And I just upset and frustrated with the world, got in an argument, and had an ill-advised argument with the fight with the coffee table that had a stone top. Wham, wham, wham. It definitely hurt. Don't do that. And over time I had to learn other ways to focus or clear that practice. And origami is a good one. I really used it a lot for a little while when I was frustrated, and I still do, because it's very easy to find a piece of paper and do it, and you can get stuck in that. So, and you don't have to learn all the complicated stuff. You can learn a pretty. Crayon is about as complicated as you need to learn, and then you're good to go. So we fold all those in. Some will show you folding this top kind of like this top triangle part. We need the crease there, so but you should probably fold it back this way. It's not that we couldn't unfold it, but we want the more stabilized in the center, so we did that. And then you're going to open these up. And this is like the cool part of the bird base. Whoever at some point designing origami or playing with these things, figured it out. Figured this out. So you take this top piece, right? You got these two down here. And you open it up. And you kind of have to fidget with it. That was a dog. I don't know if she'd really like this. You don't add any new creases in the process. There were just creases you had, and you just have to sort of clean it out and you get it down. When you get it down, it should be nice and flat. Good. And you turn it the other way. And that's so good. This one's not turned out so bad. Nice and even. It's cool. It's fun to play with now, right? Alright, so we're going to do the next round of folds. They're all the same. It's going to be right here. These are technically, I think, for the legs. Well, no, it's for the tail and the head. I'm acting crazy. So you're going to line, we're going to take this top one, see? Not both, the top one. Line this side up with the middle. Paper's getting a little thicker now, so you really have to hold it in place a little bit before you get to creasing it. Somewhere in these folds, on these, is when I generally make the most goober mistakes, or it seems to. It was usually something earlier, like I didn't tear it as cleanly so it wasn't perfectly square, or something else proper. One early mistake will compound itself through the ranks of it. But a lot of times it happens right there. Periodically, when I have it, I do some silver jewelry out of it with this clay that it's kind of cool. But they're very small. There was one girl I taught, I think that was Frances Palumbo. Sorry, Frances, I didn't mean to tell you that. That was like at Jewish school, and she had done it a lot growing up. I think, and she could make the tiniest little things, just absolutely exquisitely small. It was cool. She got so excited when we did origami for a while. That was like 7th grade pre-algebra class. We had fun. On Fridays. Let's see, here we are. Okay, so we're there. We got that point. All right. I always think this is kind of cool shape structure here. The way these angles worked out. It just has a nice pleasing shape to it. There's definitely some cool ratios involved in it. We can discuss that, but I think we're good to go on all those things. And now you're going to take this top part, fold it down, nice and happy, turn it over, and do the other side. And hey, those look like wings. Put them back up. It is. Whew, I can't think straight. Before we do that, that won't go away though. That'll be good. You're going to take both of these, and you take one, and you bring it all the way up till it can't fold anymore, right there, right? And then you fold it. It doesn't really matter whether it's here, 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 here. It's just sort of the shape you want. I do it kind of about like so, maybe. And then the other one you do the same if you want. The way these work here, this is more just stylistic on where the exact angle is. It's important to go all the way up to there though. And then you bring them down. And now we're going to do an inside reverse fold, which is a complicated name, but some people fold it back the other way too. But it's always fun to do when you get it. So you open it up a little bit, and you take this part and you push it that way, and as you push it this way, you like fold it back in on itself. Right. Inside, whoops. Fold it back in on itself, right? And you turn it over. Get this other one. You do the same thing. Don Tripp stuck in my head. Been listening to him for 2 days straight, I think. Dude is like, speaks so much truth, and it's great. Barely even recognizing his hometown. It's cool though. It's cool. So yeah, you can see where I messed up in here, right? I always do that. So you got these two sides. And one of them gets to be the head. It doesn't matter too much. And you do another inside reverse fold. This is usually an easier one to do. And that one doesn't matter the angle so much either. Kind of just how you feel like you're making it look. Now these two parts were the wings. Alright. And you pull it up. And we're almost there. We're kind of getting there. It's looking like a crane, but if you really want to set it off, you can pull them apart a little bit. Should pull apart. I just got real tired. So there is a crane with a broke tail, man. It was doing well until that point.